Hello. Today we're going to continue our discussion on bonding, and in particular, we're going to talk about covalent bonds. So previously we were discussing ionic bonds where electrons are transferred between two atoms, and today we're going to talk about covalent bonds where electrons are shared between two atoms. So a covalent bond is a type of bond in which the octet rule is satisfied when atoms share valence electrons. So again, we're following the octet rule, so we want to make sure that every atom has 8 valence electrons. But instead of transferring electrons in order to achieve this, atoms are going to share their valence electrons. So the shared electrons are counted in the octet of each atom. So let's look at the example of fluorine, and a fluorine molecule contains 2 fluorine atoms. So its chemical formula is F2. Now remember, fluorine is in group 7A on the periodic table. So a fluorine atom will have 7 valence electrons. So here we have 2 Lewis symbols or structures for fluorine atoms. And you'll notice that each fluorine has an unpaired electron. So what we'll see is those 2 unpaired electrons are going to team up and form a shared pair of electrons. So that shared pair is going to be counted in the octet of each atom. So for instance, I'm going to draw this a little bit bigger off to the side. And then I'm going to draw the other fluorine atom in blue. And then I'm also going to draw blue on top of the red there because those are shared electrons. So we could draw a circle around the fluorine on the left with its octet of electrons, so it has 2, 4, 6, 8 electrons. But those shared electrons also belong to the fluorine on the right. So that fluorine also has 8 valence electrons, 2, 4, 6, 8. And so this would be our fluorine molecule. So the atoms sharing one or more pairs of electrons are each attracted to the shared electrons, and thus are attracted to each other. The attraction to each other is called a covalent bond, and the covalent bond may be represented by the shared pair or by a single line between the bonded atoms. So we could also draw this as 2 fluorine atoms with a line between them, and that line represents 2 electrons. And then we'll also draw the valence electrons that are still hanging out. So again, that line it represents 2 electrons that are shared. So this is what we call a Lewis structure for a molecule. And next week we'll talk more about Lewis structures and how to draw them for different molecules. All right, so another way to think about the sharing of electrons is in terms of orbitals. So the sharing of electrons takes place when electron-containing orbitals of atoms overlap with each other. So an example of that would be a hydrogen molecule which contains 2 hydrogens. So it's H2. So down below in figure A, we have two separate hydrogen atoms, and remember hydrogen is in group 1A, so each hydrogen atom has one electron. And then once the orbitals get close enough to start to overlap, those two valence electrons are going to come near each other, and then in figure C, those two electrons are shared between the two hydrogen atoms. So you'll notice that now this molecule, we have two electrons that belong to the hydrogen on the left, and then two electrons that belong to the hydrogen on the right. And remember that every atom is trying to become like a noble gas. And for hydrogen, the nearest noble gas is helium, which has two electrons. So both of these hydrogen atoms now have two electrons, and they are sharing them, but that's okay. And that means that both hydrogen atoms here are happy because now they both have two electrons like helium. Now, electron sharing resulting in covalent bonding can occur between identical atoms or between different atoms. So molecules such as chlorine, oxygen, and nitrogen are formed when electron sharing occurs between identical atoms. Molecules such as water and then methane, which is CH4, are formed when electron sharing occurs between different atoms. So let's actually draw some of these structures. So Cl2, we have two chlorine atoms, and they each have 7 valence electrons because they're in group 7A. So very similar to fluorine, these two can pair up, and we'll just draw a line between them. And that would be our chlorine molecule. Now we can do the same thing for oxygen, but oxygen has 6 valence electrons. Now in this case, each oxygen has 6 electrons to start, but each atom wants 8 electrons. So we can start pairing up these unpaired electrons. And when we draw that first line, now each oxygen has 7 electrons. So if you want to count just to make sure, so if we look at the oxygen on the left, we have 2 electrons on the top, 2 electrons to the left, 1 on the bottom, and then it's sharing 2 electrons with the other oxygen. So that's a total of 7. So these oxygens aren't quite happy yet. They do need 8 electrons, so we can share these 2 electrons on the bottom. So I'm actually going to redraw this because that looks a little funny. I'm going to move that pair of electrons up. And what we have here is what's called a double bond. Now before, with chlorine and fluorine and hydrogen, we just had a single bond between the atoms. But sometimes atoms will have a double bond or even a triple bond in order for everything to have 8 electrons. So for nitrogen, and I'll draw nitrogen down below, each nitrogen atom has 5 valence electrons, and each one wants 8. So we can start pairing up those lonely electrons. And I'm drawing a very silly figure here. So what we'll actually do is draw this as what's called a triple bond. Kind of clean up our figure here. And if we draw circles around each atom and the electrons that they own or co-own, we can see that each nitrogen has 8 total electrons. So they're sharing 6 electrons, and then each nitrogen has its own pair of electrons. So each nitrogen has 8 total electrons. Now, we can only go as high as a triple bond. We cannot have a quadruple bond, for instance. So really the only type of bonding that you can have for covalent bonding are single bonds, double bonds, and triple bonds. Now, what about water and CH4, which is methane? So let's draw water. So we'll start with our oxygen. And remember that has 6 valence electrons. And then we'll draw 2 hydrogens, which each have 1 valence electron. And we can see that oxygen can share electrons with each hydrogen. And now oxygen, so I'll draw a circle around oxygen. Oxygen has 8 electrons. And remember, hydrogen only needs 2 electrons because it just wants to be like helium, which also has 2 valence electrons. So the hydrogens are happy. They don't need an octet. Okay, so that would be our structure for water. And you don't have to draw those circles. That's just to show who owns what electrons or who's sharing which electrons. Now for methane. So carbon is in group 4A, so it has 4 valence electrons. And then there are 4 hydrogens, which each have 1 electron, so we can start placing those around carbon. And then we can draw lines between those electrons. And now each hydrogen has 2 electrons that it's sharing with carbon. And carbon has 8 electrons. So at the top it's sharing 2, to the left it's sharing 2, on the bottom it's sharing 2, and on the right it's sharing 2. So that would be a total of 8. So these are just a few examples of what are called Lewis structures, but you can see how these different atoms share electrons in order to become like a noble gas. Your textbook has a table that shows a few other molecules. So we went over nitrogen, we also went over methane, and we looked at water. But in addition to that, this table shows carbon dioxide, formaldehyde, which is used to preserve deceased bodies, just to put it mildly there. Ammonia, which is used as a cleaning agent, and oxygen difluoride at the bottom. And this is a really cool table that also shows how we draw the Lewis structures, so how electrons pair up. Now, how do we name these covalent compounds? This is pretty similar to how we name binary ionic compounds. So we start by naming the least, what's called electronegative atom or element. And I don't believe we've talked about electronegativity yet, but elements have different attractions to electrons. But what we'll write here instead is we're going to name the first nonmetal, and we're just going to use the name of the nonmetal as it is. And then we're going to add the stem of what's called the more electronegative element. So we'll just say the second nonmetal. Plus IDE. Now, in addition to that, we also need to indicate how many of each element we have. So we're going to use a prefix in order to tell someone how many of each element exists in a molecule. So up above, I'm going to write CO2. So we'll do that as an example. So again, we're going to start by writing the first nonmetal name, which is carbon. And we don't have to change the name at all. And then we're going to name the second nonmetal as we would in a binary ionic compound. So the oxygen becomes oxide, but we want to indicate how many oxygens we have and how many carbons we have. So we're going to use prefixes. We have 2 oxygen atoms, so we're going to use the prefix di. So this becomes carbon dioxide. Now, we're not going to include the prefix mono in front of carbon. So just a note down below, the prefix mono is not used when it appears at the beginning of the name. So for carbon dioxide, it's just understood that carbon is by itself because we're not including a prefix. However, what if we just had CO? So again, we would call this carbon, but instead of dioxide, we only have 1 oxygen, so we're going to call this monoxide. Notice I dropped the second O there, otherwise it would look like monoxide. So it's just going to be monoxide. So we do use the prefix mono if the second nonmetal is by itself, but we don't use the prefix mono if the first nonmetal is by itself. Okay. So let's do a few more examples here. In the first example, we have SO2, so sulfur and oxygen. So we're going to name the first nonmetal, which is sulfur. And then we have 2 oxygens, so that's going to become dioxide. And again, we don't use a prefix for sulfur because it's the first nonmetal and it's by itself. All right, now for the second example, we have an element called xenon. And then we have 6 fluorines attached. So again, we just start by naming the first nonmetal, which is xenon. And then fluorine is going to become fluoride, but we have to indicate that there are 6 of them. So let's go back to that table. So if we go down this table to 6, the prefix is hexa. So we're going to put hexa in front of fluoride. So this is xenon hexafluoride. And then CO2 we already went over, so this is carbon dioxide. And then our last example, we have carbon and 4 fluorines. So this is carbon, and then fluorine becomes fluoride, but we have to figure out what the prefix will be. So let's go back. And if we go down this table, the prefix for 4 is tetra. Okay, so we have carbon tetrafluoride. So it's a good idea to kind of go through these prefixes and just know all of those prefixes, 1 through 10. So we have mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So sometimes it's easy to get hexa and hepta mixed up. So you might want to focus on those two in particular. I can also post some flashcards for these prefixes as well if you haven't seen these before. Usually we only have like 1 through 6 of any element in a compound. It's very rare that we're going to see 8 of something or 9 of something or 10 of something. So I still would want you to know all of those prefixes, but the most common ones are the first 6 approximately. And then here is the solution slide. And I think we're going to stop there. Next time, so probably next week, we're going to start drawing Lewis structures for covalent molecules. We already did a few molecules, but we'll kind of look at some more complicated ones as well. So I will see you in the next video.